start by talking about charges and forces. Now, you know matter is made up out of charged particles. You know that. And you know that you can charge things by rubbing them. You've experienced this. And you already have some sense as to the way charges work. And you know that matter is made up out of charged particles. And you've played around with this before. You've seen it in school. There's a summary of all the things that we have to say about charges in the textbook. Looks like this. Don't write this down. Okay, don't write this down. You can take a look at that in the book. That's a summary of our whole charge model. It's all the details. Usually we're going to try to sum it up, not in terms of words, but in terms of pictures. It's a better way to look at it. Matter is made up of plus and minus charges. You can separate them. There's forces between charges. If I have equal charges, the force between them is repulsive. If I have opposite charges, the force between them is attractive. The force decreases with distance. This is all stuff you've seen before. But I'll show you a couple of examples of this. This is something that people have thought about for a long time. People have thought about this for a long time. The Greeks were the ones who did the first experiments with charged objects. And they discovered that if you took a plexiglass rod and rubbed it with polar fleece, it developed a special property. As a matter of fact, if you took that rod and you rubbed it with polar fleece and you brought it near a styrofoam packing peanut, the styrofoam packing peanut would actually be attracted towards it. And heavens, this one even sticks, and it looks like it wanted to slide down too. There we go. And so they discovered this attractive force. In fact, they saw this with amber and with cloth and with like little bits of feather, little bits of paper. But I'm doing something to this. I'm charging it. And the question was, are you transferring something to it? What am I doing to it? And actually, you know, in fact, what's happening now. As I'm rubbing this, I'm actually tearing molecules apart. I'm tearing molecules apart. And I'm leaving positively charged ends and negatively charged ends. And one side stays positive, one side stays negative. And so this thing gets charged up. And because it gets charged up, it's going to exert this charge force on things. And this charge force, there we go. That's better. Charge force is kind of a new force of nature. And it seemed kind of magical. These things kind of like jump up. Okay, they don't jump up, but they could. So they will be attracted to it. There was this attractive force. And so the Greeks figured this out. Now, this was worked out in the Victorian era, too. People used to invite folks over to their houses and have like parlor games that consisted of tricks with electrostatic forces. For instance, you can take a CSU pom-pom and rub it with a pair of silk boxer shorts. And if you do that, you develop an electrostatic charge on this pom-pom, and it gets all kind of like this. And the little strands of the pom-pom will be attracted to my hand, which is kind of cool. And so I have this charge force. And again, you get it by rubbing. And I'm transferring charges. Something about the rubbing makes those charges develop. Okay? Now we can get the most charges of all using this device right here, which is a Van de Graaff generator. And the Van de Graaff generator builds up a charge in a completely different way. There's a little comb in the bottom that basically puts charges on the belt. They come up to the top and they hit this sphere at the top. This sphere is a conductor. And what do you know about electrical conductors? When a charge hits a conductor, it's free to move. You know that about conductors. That's what we mean by a conductor. The rod is an insulator. The charges stay put on the rod. But this is a conductor, and so the charges are free to move. And what would you expect that the charges would do? They hit this dome. They hit it. They repel each other. It's going to be negative charges that go up to the top. What would you expect them to do? What's that? They'll go to the surface. They want to spread out. They want to get as far apart as they can. And so they'll go to the surface. They'll spread out. This whole thing is going to be coated with negative charges. And if I put pi tins on the top, pi tins are conductors. So some of the negative charges are going to go from the sphere onto the pi tins, because this is a conductor. And they're trying to get as far away from each other as they can. So they'll go up onto the pi tins. Well, then the pi tins have negative charges. What would you expect them to do? Fly. Oh, yes. We're going to expect them to repel each other. And you know this. You know this about charges. And in fact, they charge up, and the things fly off the surface. This is like Balloon Boy all over again here. There's my flying saucers. Oh, yeah. And they'll travel like that. And it's because they're charged. The classic thing, though, that people do with a Van de Graaff generator is this. If you fire it up, you put your hands on it, your hair stands on end. And I don't do this in class because people want me to do that. Like when people come by and want a picture of me for whatever purpose, they say, do you have one of those balls and you put your hands on it and your hair stands on it? Can we take a picture of you like that? And I feel stigmatized by that, so I'm not going to do that. But this will work the same way. I have a little Van de Graaff generator with, little bits of pink hair on it. And if I fire this up, what will happen is charges will travel out those strands of hair, and they get negatively charged, and so they're going to stand up. And if I bring them down so they get chargy, they clearly repel. And this happens for the same reason that your hair stands on end. Negative charges, they're going to go onto the strands. Where would you expect them to go on the strands? They go onto the tips. They go onto the tips. They want to be as far away as possible. And so they tend to be pretty chargy out here. If I bring my hand near it, you can see this thing is attracting me. It's because the charge is spread out and you get this repulsive force and it makes this effect happen. Now, at an atomic level, something like this is happening. When you charge things by friction, when you rub them together, you're actually tearing molecules apart. You're actually tearing molecules apart. It's quite remarkable. When you rub them, you get these big molecules, tear them apart, you end up with a positive end and a negative end. And that's where the charges come from. So the friction, when you rub your feet across the carpet and you get charged up, you're actually tearing apart molecules in the carpet and in your shoes. It's really quite something. And all these things that I was doing up here with the rubbing different things, it's actually tearing molecules apart, and you end up with charges because of that. Now, another place where you see it is with tape. If I pull tape off a roll, I'm tearing molecules apart because tape's sticky, and the molecules are kind of like bonded together. When I pull the tape off the roll, I rip them apart. And when I do that, the tape ends up getting a charge associated with it. And so the tape will charge up when it comes off the roll. Okay? Tape coming off the roll gets charged up. And here's how I can tell it's charged up. The tape's charged, and I know that because it's attracted to me. And you've seen this before, right? You pull a big piece of tape off a roll, and you're trying to do something like a craft project, and it like sticks to you, or it sticks to whatever you're trying to tape, and you've got it like stuck to you, and you're doing that. You're trying to get it off. My hypothesis when I was a kid was this. The tape is sticky. And I thought tape has this long-range stickiness force attached to it. It wants to reach out to things and stick to them. And it will actually seek out things to go to. That was my theory. But I have a more finely developed theory now, which is that the tape is charged. I'm a conductor. And I'm also made up of molecules which have positively charged centers, negatively charged electron clouds. And the negative electrons, they can move because I'm a conductor, but even if they can only like slosh to the side, even if they just slosh to the side, I can still have a charge separation that exists. And that'll produce an attractive force. And so the tape is going to attract me, even though I'm neutrally charged, because of the fact that it is charged.